Good morning. Today I will take the subject on high performance liquid chromatography, or commonly known as HPLC. This is one of the most important techniques, both in food analysis as well as in pharmaceutical analysis. So, in the class on chromatographic techniques, I told you a little bit about column chromatography. Now, today we will talk in detail and you will understand the nuisance of high performance liquid chromatography. So, high performance liquid chromatography, you will find this technique and the instrument almost in every research laboratory and in every analytical laboratory. It is used widely by the industry, both in quality control and in quality assurance. And the reason it is used is that you can separate a variety of chemical constituents and analytes by mixtures using this technique. You can do quantification, you can find adulterants, you can find contaminants. And HPLC, coupled with mass spectrometry, known as LCMS, and the LCMS-MS, is a very powerful tool to identify new compounds and new analytes. So basically, in food analysis, it can be used to detect and quantitate any of the constituents that you have studied till today. These include carbohydrates, amino acids, proteins, sugars, vitamins, nucleotides and nucleosides, fatty acids, aflatoxins, antioxidants, contaminants, pigments, food additives, as well as they are used in enzyme assay. So this is just a small list of what can be done in food analysis. So what are the advantages of HPLC? One is the basic advantage is that high resolution. The difference, the way you can separate two components of a mixture, and the other is the speed of analysis. Two, the HPLC columns, if you look after them well, can be reused for several years without repacking or regenerating. And these packed columns, which are automatically packed, give reproducible results, unlike the other column chromatography. There is easy automation of the instrument, where now with the auto sampler, you can just load the samples ranging from 96 to 384 or more samples in a carousel and leave. You can come back in the morning and look and analyze the data and set up a new set of analysis. The only tedious and time-consuming procedure in HPLC is the sample preparation. After sample preparation, everything is automated. And you can upscale this to preparative procedures and also use this to prepare pure compounds, isolate and prepare pure compounds. The other two advances that have made HPLC such a universal technique is that the particle size that they use in the columns is growing smaller and smaller. As a result, the resolving power is increasing. And the other one is the use of very small amounts of solvent because they are pumped in and the column volumes are so small. So this is a schematic of a simple HPLC system, which consists essentially of a solvent reservoir. It contains a pump to manage the flow rate of the solvent. And also, if we want to make a gradient to control the flow of more than one solvent, you have an injector or a sample loader through which the sample is loaded. Then you have the column, the HPLC column, which is filled with packing material, which is the heart and soul of a HPLC system. So if you want an effective HPLC system, you must take care of your HPLC column. And then you have a detector to detect the analyte, and then you have a data system or a computing facility to look at the results of the separation and do any calculation that is required. The solvent that passes through the column is collected in the waste. So this is what a typical HPLC system is. What you saw in the previous slide was just a diagrammatic view. So here you have all the parts of the equipment which is put into a compact instrument, and you have the computer through which you can look and control the complete operation of the system, even the injection. There is no manual intervention other than filling the solvents or changing the columns. So just to recap and bring you back into what is chromatography, it is an interaction between the analyte or the solute and the stationary phase and the mobile phase. So separations take place because of the differences in the interaction between the solute and the stationary phase and the solute and the mobile phase. So this differential interaction of the analyte with the stationary phase and the mobile phase is the one which leads to the separation, and analytes can be analyzed. Now, as we go along, we will see what are these properties, or what are the forces of attraction between the solute and the stationary phase, and the solute or the analyte and the mobile phase. So the difference between column chromatography and planar chromatography is, the commonality is that they both use a stationary phase and a mobile phase, but the difference is that in column chromatography, the particles are packed into a column, whereas in planar chromatography, either they are in a thin layer or in the form of paper. So let us understand this chromatographic separation. So if you have a chromatographic column and we put a mixture into it, after passing the solvent or the mobile phase, you will see that the analyte has separated over here as shown into three components: a yellow color, a red color, and a blue color. So these bands, as you see, move as separate bands or individual bands at different speeds. So what dictates this speed? It is the competition between the mobile phase and the stationary phase for the analyte. Here in this figure, the yellow dye is attracted more to the solvent or the mobile phase rather than the stationary phase, and so therefore it moves faster and closer along with the mobile phase. On the other hand, the blue dye over here has a little attraction for the mobile phase, but has more attraction for the stationary phase or the column packing. So it remains longer on the column packing and tends to move much slower in the column. The red dye, compared to the yellow and the blue, is of intermediate order. So therefore, its attraction to the solvent and to the stationary phase are almost equal. So therefore, it moves at an intermediate speed. So the separation of the analytes is based on or depends on the attraction of the analyte to the solvent or to the stationary phase. And this separation that you get is known as a chromatographic separation. So this you can visibly see in the diagram. So you put a mixture, and as the mixture moves along the column, depending on its attraction to the stationary phase and the mobile phase, they will elute as compact bands. And when they elute, they are detected in the detector and converted in, into a signal which you can see as triangular peaks, or what we say as Gaussian peaks. So you get a red peak, you get a blue peak, so that you see the separation. So basically, this is what happens in a chromatographic or a column chromatographic process. So the separation modes, that is the properties which bring about the attraction between the solute and the solvent, or the solute and the stationary phase, are basically due to the polarity, due to the electrical charge, and due to the molecular size. When we spoke on chromatographic techniques, I talked about the electrical charge or the ion exchange chromatography, where you have positively charged stationary phase, and if you put a sample, if the sample is negatively charged, it will be attracted to the stationary phase. Similarly, on molecular size, we saw that it is a sieving technique where it can, the molecules or the analytes will separate based on size. So the big molecules cannot enter the pores and they will elute first, and the smaller molecules will remain in the column and elute later. But in the current HPLC techniques, it is the most popular mode by which the separation takes place and use is because of the polarity. So what is polarity? Polarity is the property of a substance where the positions of the electrons at different points gives rise to negative or positive poles. It doesn't give for the charge. It gives rise to positive and negative poles. So you see here, water is polar because it has got the both negative and positive poles. Methane is non-polar. Acetic acid is polar. So then when you look at the miscibility of solvents, you see that polar-polar solvents will mix, whereas polar non-polar solvents are immiscible. The polar and non-polar property of a solvent can be compared to that of water and oil. You know that if we pour oil into a tube of water or a bucket of water, the oil will float. The two are not miscible. So the polarity of the substances, which gives rise to either the positive or the negative polarity, is responsible, or the most used uh, property of the stationary phase and the analyte, which is used in HPLC, or high performance liquid chromatography. There are four basic types of separation in HPLC, and these are: one is the liquid solid chromatography, where the mobile phase is a liquid and the stationary phase is a solid. So there we have normal phase and reverse phase. Then you have liquid-liquid chromatography, where the stationary phase is a liquid and the mobile phase is a liquid. And there also we have normal phase and reverse phase. Because of the charge, we have ion exchange chromatography, and also we have gel permeation chromatography, known as size exclusion, gel filtration, or it is even known as sieving chromatography. So in adsorption chromatography, a solid such as silica gel, what you see over here, is used as the stationary phase. And the differences mainly in the degree of adsorption to the surface are used to separate the solutes. So adsorption is a liquid solid chromatography, and the retention strength depends increases with the hydrophilicity of the solute. Okay. Then you have ion exchange. We have seen the same slide in the previous webinar on chromatographic techniques, where the column material is either an anion exchanger or a cation exchanger, which is positively charged or negatively charged. The anion exchangers attract negatively charged molecules and then can be displaced by a solvent which has more positively charged molecules. And you have the cation exchangers. In these columns, the disadvantage is these columns after the experiment have to be regenerated. And then you have size exclusion or gel filtration, where the separation is based on size because of the pores on the column material. So the small molecules enter the pores, the larger molecules remain in the interstitial spaces, they move along with the solvent, and the analytes get separated according to size, the big molecules coming out first and the small molecules at the end. So now let us talk more about liquid-liquid chromatography, which is the most widely used HPLC technique. So in liquid-liquid chromatography, if you recollect, it is the liquid. A liquid is put or coated, a stationary, an inert stationary phase is coated with a second liquid, and this liquid will be immiscible with the mobile phase, and the separation occurs because of the solubility of the analyte, the difference in the solubility and attraction of the analyte to this liquid, which I have shown in red here, and to the liquid which is passing through the column. So here the mode of separation is partitioning. So the analyte gets partitioned between this liquid and the mobile phase that is moving between the thing. So the separation is based on the analyte's relative solubility between the two liquid phases. So in partition chromatography, we have two types of chromatography. One is the reverse phase chromatography and the other is the normal phase chromatography. In normal phase chromatography, the stationary phase is polar, such as silica, or any other chemically bonded surface, such as the diol or the cyano. And the mobile phase is non-polar, generally hexane or ether. Reverse phase is the exact opposite of normal phase and therefore termed as reverse phase. So here the stationary phase will be non-polar and the mobile phase will be polar. So generally in the reverse phase you have a chemically bonded silica with large arms such as C18, that means 18 carbon, or C8 or C4, or a phenyl. And the mobile phase is generally a polar solvent such as water plus an organic modifier. And this is more often used in the analysis, in food analysis, and several other techniques. So you will come across the term RP HPLC. RP is for reverse phase HPLC. So now just let us look at what happens in normal phase and reverse phase. So in normal phase, the stationary phase is polar, the mobile phase is non-polar. So now when you put a mixture of samples onto the column, the more polar compounds will interact strongly with the stationary phase. The non-polar will not interact with the stationary phase, and so therefore the polar components will move very slowly, which is shown in yellow, and the non-polar component will move out fast. So that means the non-polar will be eluted first and the polar will be eluted later. So here is a polar stationary phase. That means you just have silica, and these OH groups actually subscribe to the polarity of the phase. You can also have some diols, or you can also have some cyano groups on it. So that is the polar portion of the silica or the packing material. Now, reverse phase, as I said, is exactly opposite. So now look at the figure. You have the exact opposite of what you saw in the previous figure. So we have blue eluting first, followed by red and yellow. And now we have the yellow eluting first, followed by blue eluting last. So here the stationary phase is non-polar, the mobile phase is polar, the non-polar component moves more slowly, so therefore it will elute last, and the polar component moves more rapidly because it will not interact with the stationary phase. So the polar will elute first and the non-polar will elute the, and this is the exact opposite of normal phase chromatography. So in reverse phase hydrophobic, what happens? So if you look at a column, the column will be surrounded by the polar solvent, and polar solvents, generally the solvents will contain water, and so they are actually bonded together by a network of hydrogen bonds. Now, when a nonpolar analyte passes through the column, what it does is it the network of hydrogen bonds between the solvent passing is broken. The nonpolar substance is pushed to the nonpolar location because of the nonpolar interaction, and the polar analytes of this will be soluble in the water and will elute. So this once again shows you the reverse phase mechanism, where A is the more polar analyte, it will not be attracted to the stationary phase, and B is the less polar analyte, or it is the non-polar analyte, and it will be attracted, or it will stick to the stationary phase, and it will elute later when methanol or water is the solvent. So the relationship now between the polarity and the retention time is when you use a reverse phase column. So you see, when you have a non-polar substance such as a phenol, and you have a C18 column and that of methanol, the phenol or the polar substance will elute first, so the retention time will be lower, whereas the non-polar compound will elute later and the retention time will be longer. So in a reverse phase column, the more hydrophobic or the more non-polar substance will elute much later than the polar. So in a chromatogram, the first part will be the polar compounds and the last part will be the non-polar compounds. So to summarize, you have in normal phase, the stationary phase is polar, mobile phase is non-polar. In reverse phase, the stationary phase is non-polar and the mobile phase is polar. Now we know the basis and the mechanism of separation by reverse phase and normal phase. But how does a chromatographer like you or me choose the appropriate phase, the stationary phase and the mobile phase, to achieve a separation, a HPLC separation? So there should be some means for us to know. We cannot do it by just like throwing a dice by chance. There is a basis of separation. So now, which technique should I use? Should I use normal phase or should I use reverse phase? Which column should I use? Should I use C18 column or C8 column or C4 column? Which solvent should I use? Should I use methanol or should I use ethanol or acetonitride? And then Should I use an isocratic elution or should I use a gradient elution? These are several of the questions that one needs to answer before starting, or you need to understand before starting a HPLC experiment. So if you look at the analytes, you have to study their polarity spectrum. So you have to know some information about the structure and the nature of the analytes that you are interested in separating. So you need to know the functional groups, you need to know the structure, and based on that, you can tell whether the analytes are polar or non-polar. So if you look at the aliphatic molecules, such as the aromatic hydrocarbons, the halogenated hydrocarbons, the aliphatic hydrocarbons, and things, these are all highly non-polar. Whereas if you look at molecules such as acids, alcohols, salts, compounds having OH, COOH, and things, these are all polar molecules. So organic molecules can be sorted into classes according to their functional groups. And based on that functional group, the separation mode based on chromatography is largely determined. So we need to know a part of their functional groups. Next is we need to combine the proper mobile phase and the stationary phase to get the separation. So in the chromatographic separation, now that we know the structure of the analyte that we want to separate, we need to create a competition between the analyte and the stationary phase and the analyte and the mobile phase. So the competition is between the mobile phase and the stationary phase for the analyte. Then the compounds in the sample, which are similar, if they are similar to the stationary phase, will be delayed. If they are opposite in polarity to the stationary phase, they will elute first. So if we look at thing, then we also need to understand the polarity spectrum of the mobile phase. So which of the solvents is a water-loving solvent or a polar solvent, and which of the solvents is a water-hating or a hydrophobic solvent. So water is at the polar end. Hexane, methane, hexane, methylene chloride, benzene, these will all be at the non-polar end. And then you have the in-between solvents such as acetonitrile and tetrahydrofuran, which can be used to mix the polar and the non-polar. So which end of the scale represents the strongest mobile phase depends upon the nature of the stationary phase. So we have seen that when we use a polar stationary phase such as silica, we will use hexane as the solvent. And when we use C18 or a non-polar one such as C18 or the C8 or C4, we will use the solvents at the polar end. Now, for the thing, we also need to know and understand the polarity of the stationary phase. So as we said, you have two types of stationary phases. One is the bonded stationary phases, which have C18 or C8 also. So here you see C18 is the most hydrophobic uh, bonded phase, which is highly nonpolar, whereas silica has the OH group, active hydrophilic group, and it is the water loving surface. And in between, you have the cyano, you have phenyl, you have octyl, and so on. So the once you know the polarity of the stationary phase, you know the polarity of the mobile phase, and you know the polarity of the analytes, you can develop and put together a reverse phase HPLC separation. So now putting these two together, that is the analyte chromatographic polarity spectrum. Again, as we said, you need to know about the analyte. You need to know whether it is a hydrophobic analyte or it is a hydrophilic analyte. So look, the best example I can tell you is about vitamins. You have the water soluble vitamins and you have the fat soluble vitamins. So, if you want to do a fat soluble vitamin separation, we will generally use the reverse phase. And for water soluble vitamins, as such, we will tend to use either a reverse phase or a normal phase. But in a reverse phase, when we use it, we'll use a solvent such as water because the vitamin will have greater attraction to the water. So, to summarize, you must choose the best combination of a mobile phase and a stationary phase with appropriately opposite polarity. Then, as the sample analytes move through the column, the rule like attracts like will determine which analytes will slow down and which analytes will move at a faster speed. In other words, which analyte will elute first and which analyte will elute later from the column. So how do you select the column? So here is an example. Look, this is there are two molecules. One is anthracene and the other is 3-hexyl anthracene. We want to separate these two substances. Now the structural formulas are available and we look at the structural formula, you see that anthracene and hexyl anthracene have the same basic structure. The difference between them is hexyl anthracene has got this hexyl group on this ring. And we know that a hexyl group is hydrophobic. And so, therefore, this suggests that we can use a C18 column in the reverse phase to separate these two because the attraction to the C8 will be different between the two. This will be attracted more, whereas this will be attracted less. So now when you use a solvent, a polar solvent to separate it, anthracene will elute first and 3-hexyl anthracene will elute later. So if you know the structures, you know which is going to elute first and you can also choose the column accordingly. And you will see here, we can choose the C18 column. We can also choose the C8 column. But if you look at this structure, C6, it will have very high interaction with C8 and it may be very difficult to remove it from the column, to dismantle this attraction between 3-hexyl anthracene and the C8 of the column. So the modes of high performance liquid chromatography, you are reverse phase. So you use C18, C8, C14, cyano or amino columns. The mobile phase will be water and organic modifiers. If you are using ion pair chromatography, which is similar to reverse phase, you can use C18 and C8. Here, water and organic ion pair reagent. Compounds which are not soluble in water, we use a normal phase. So you can use again the silica, the amino column, the cyano column or diol, and the mobile phase will be an organic. In ion exchange, it will be an anion or cation exchanger, and we use only aqueous buffers. In size exclusion, we will be using polystyrene or silica beads, and here again it is the disadvantage is you can only do aqueous separations. You can use only aqueous solvents. So now that you know about the mobile phases, what else should you know for HPLC before optimizing or before starting an experiment? You need to know and understand what is the column. Which column are you going to use? What is the size of the column that you're going to use? What is the diameter of the column you're going to use? What is the particle size of the column you're going to use? And what is the pore size of the particles that you are going to use? So it is very important to know this about the column. And all this information will be printed on the column. So C18 indicates it's a bonded phase. It could also be written as octadecyl, which is the same as C18. So anything which says octadecyl or C18 or carbon 18, it is a reverse phase column. The first number here, it is 4.6 millimeters internal diameter and 250 millimeters, or this is the length of the column. You have, as we will see, you can get different diameter columns and different length of the columns, which will affect the resolution of that. Then you have particle size. The particle sizes can range anywhere between 1.7 microns to about 30 or 100 microns. So how does particle size affect the separation? And then you have pore size. This pore size, the pore size that you use will depend on the molecular mass or the structure of the analytes that you are going to separate by the HPLC. But please remember and look, if today when you're doing, you can go back to your laboratories and look at the column and see whether all these are given. And in any publication or any procedure, you will see that the column size, the length and the width, the particle size and the pore size will be given or will be printed on the column. So to give you an idea of what is uh, the size of a particle, what we say as particle size. So when we say a 5 micron particle size, the diameter of the column of the particle from one end to the other end is about 50,000 angstroms. And so now here you can fit 166,300 angstrom pores across the equator of this particle. So here are the different columns that you can see. Columns vary in length, in diameter, and in the particle size and pore size. So the solid support, which is inside, most of the HPLC columns are steel columns, which are filled with particles or size or ranging, as I said. Now the columns which we use in LCMS MS is 1.7. So LC in LCMS MS is nothing but high performance liquid chromatography or ultra performance liquid chromatography. So they vary in particle size. These particles are bonded phases, or they are chemically bonded with C18, C8, cyanidol. And this chemical bonding, the advantage is you get reproducible results. Along with the main column, we use sometimes a guard column, which is used to protect the analytical column so that any large particles will be trapped by the guard column. The guard columns are less expensive than the analytical column. So if there is a problem in separation, you can just change the guard column. So the guard column prolongs the life of the analytical column, and it is the analytical column which performs the separation. So what are these bonded phases? These bonded phases are chemically bonded. So what you can see here is this is a C8, and this is the, it is showing you three C18 molecules which are bonded to the silica. And the stationary phases that are currently available and used are the C18, the C8, the C4, the C2, aminopropyl, cyanopropyl, and diol. We also have the C30 columns, which we use for beta carotene but separation, but they are very rare. So if you look at the retention time of a molecule or anything, you see that if you put the same analyte onto a cyano, a phenyl, an amino, or the, you will see that the retention time will take much longer, or it will take much longer to come out of a C18 column compared to a phenyl column. So the hydrophobicity increases from Cn to C18. So C18 is currently one of the most hydrophobic columns are available, with the exception of the C30 that we use for separating the carotenes and the carotenoids. Now let's come to particle size. What does that particle size that I told you, they range from 3 micron to 10 micron, and how does that affect the separation? The particle size of the HPLC column refers to the average diameter of the particle thing. This particle size affects the back pressure of the column and the separation efficiency. So the lower the particle size, the greater is the efficiency of separation between two analytes. However, the disadvantage is as you go down, decrease the particle size, the back pressure on the column will go up. So the particle size affects both back pressure and separation efficiency. So as the particle size decreases, the column back pressure increases, and the efficiency also increases. So we generally will go for to get good resolution, as you will later see what we mean by resolution. We use particles of smaller size. But however, you have to be sure that your sample is absolutely pure. So your purification process or your sample preparation process has to be taken has to be carried out with the utmost care. So particle size actually increases, the decreasing particle size increases the efficiency of high performance liquid chromatography. So a well-packed column with 3 micron packings produces almost 2 times the separating efficiency of a 5 micron column. However, a 3 micron column will have a threefold higher back pressure than the 5 micron column. Highly efficient small particle. Now we have less than this, the 1.7 micron, which is used in ultra performance liquid chromatography. They are ideal for separating complex mixtures with similar components. That means having very minute differences in their structure. The large particle size, the 5 micron and the 7 micron, are typically used for routine analysis. In most of the food analysis, it is sufficient to use the 5 micron column. The large 10 micron columns have got moderate column efficiency. You also have 20 micron, and these are generally used for preparative purposes, where you use columns of diameter of about 22 to 45 centimeters as compared to the internal diameter of 25 centimeters and 4.6 millimeters internal diameter. So then we have, as I said, a pore size. So what is the pore size? It actually represents the average size of the pores on each particle. So the size of the analyte should be considered when you're choosing the appropriate pore size. So molecules which have got very high molecular weight should not be used on columns with low pore size. So a pore size of 100 angstrom or 60 angstrom should be used for analytes below 3000. So in almost all the analytical procedures for food analysis, they are all less than 3000. So we generally use the columns with either 100 angstrom or 60 angstrom. So for molecular weights, for 3000 to 10,000, you use 100 to 130. And for very high molecular weight, such as the proteins, we use 300 angstrom. So the pore size actually represents the surface area. So that is for the binding of the molecule. So if the surface area is very low and it is a big analyte, this polar-polar interaction or non-polar interaction cannot take place. Then you have the carbon load. This measures the amount of bonded phase, that means the amount of C18 which is there. So columns with higher carbon load give you greater column efficiency and resolution, and lower carbon loads give you the less retentive packing. End capping is a term you will see on reverse phase HPLC columns, where a secondary bonding step is used to cover the unreacted silanols. So you see, when the chemistry is done on the silanols, not all the OH groups will take the C18 or the C12. Some of them may not, and those will now react, and you will see some sort of distortion in the peaks. So to prevent that, end capping is done, or to block all the unreacted OH groups. However, end capping costs. So if you buy an end capped column, the end capped column will be much more expensive. So theoretically, if we look at the columns, these are the different types of columns. As I said, you can get columns with diameter of 1 millimeter, 2.1, right up to 22.5, and bigger preparative columns. And you have the column length. We can go from the guard columns to about 25, and maximum are the 30 centimeter columns. So the greater the column length, the greater the resolution. The smaller the column diameter, the higher the resolution. However, the pressure will be inversely proportional. So the smaller the column diameter, the higher the back pressure that you see. The flow rates that are generally used are, if you're using a preparative column, you can use high flow rates such as 24 milliliters per minute. But if you're using the most commonly used column in food analysis or analytical labs, the 4.6 millimeters by 225 centimeter column, the flow rate is generally in the order of 1 millimeter. If you're using the micron or in UPLC, we use flow rates in the range of 0.2 milliliters per minute. So now that is what you need to know about the stationary phase. Now coming to the mobile phase, we need to understand the properties of the mobile phase and how to choose the mobile phase for a separation. So here again, the mobile phase must not interact with the stationary phase. It must be inert to the stationary phase, and the mobile phase, the analyte that you are going to separate must be soluble in the mobile phase. These two are the major criteria. That is, it should not interact, it should be inert to the stationary phase, and the analytes should be soluble in the mobile phase. And the mobile phase, we know, if the analyte is attracted to the mobile phase, it moves faster, and if it is not attracted, it will move much slower. So when choosing the mobile phase, we look at a series known as the heliotropic series, in which the solvents are arranged based on their polarity. So you see in the upper part of the table are the solvents such as pentane, hexane, cyclohexane, and these are the solvents you see which we can use in adsorption chromatography or in normal phase chromatography, where you use the silica column or the. So you look, we do not use any of these solvents, that is from pentane to chloroform to dichloroethane. We do not use these solvents in reverse phase chromatography. And then you have, in reverse phase chromatography, the common solvents that are used are tetrahydrofuran, acetonitrile, methoxyethanol, propanol, methanol, and water. And you see here, we do not use much of these. Very little in terms of the K factor is used in the normal phase chromatography. Now, how does the solvent composition affect the separation? So here are three very good examples. So if you look at this solvent, which contains 75% methanol and 25% water, as compared to that which contains 50% methanol and 50% water. So this solvent is higher in polarity than this solvent. So in reverse phase chromatography, as you increase the polarity of the solvent or you increase the water content of the solvent, you will see that the separation or the resolution is much better. However, it is slower. It takes longer for the peaks to elute. When you use a lower polarity solvent, you can get a faster separation. So you see that the separation is very quick. One of the best examples for you to understand is the separation of glucose, fructose, and sucrose on an amide column using acetonitrile water. So if you use 70-30 water, you see that almost, you cannot get the separation of sucrose, of glucose and fructose. However, if you decrease the water to 80-20, you will see that there will be separation. And sometimes, you have to increase either the acetonitrile concentration or the methanol, that's the organic modifier, with the thing. So the message here is the polarity of the eluent also affects the retention time of the analytes. And then when you elute the analyte after you have injected it onto the column, you can elute the analyte in two different modes of elution. One is the isocratic elution, where from the start of injecting the sample onto the column till it is detected by the detector, we use the same solvent. So if I use 80% acetonitrile, we use 80% to the end. If I've used 50% methanol, I use 50% methanol. That is known as isocratic elution. In the gradient elution, this is you load the sample at a particular composition of the solvent, and as the run is taking place, you change the strength of the solvent. So gradients are used generally when you want to separate molecules of very similar structure, which have minor differences in their structure. And the gradients we use can be continuous or stepwise. You can use a binary gradient where two solvents, or you can use a ternary gradient with three solvents, or a quaternary gradient with four solvents. So the currently available instruments can support binary, ternary, and quaternary solvent gradients. So in an isocratic system, this is what you see. So you have a pump, you have a solvent manager. So this same solvent is being pumped through the column till the run is complete. So it remains the same throughout the run. In a gradient system, you will generally have more than one pump. So these two pumps will control the flow rate of solvent A and B. There will be a mixer to mix these two solvents, and the concentration of the solvent will change as the run proceeds. So you start with say 100% A, and you can add B in small aliquots, and by the end of the run you can have 100% B and 0% of A. So this is what gradient is. So you can make the gradient either as a linear gradient, that means the gradient changing with constantly with respect to time. You can make a convex gradient, or you can also make a concave gradient. So here is a linear gradient where during the run you start with 2% B, and in 60 minutes you see it has gone from 2% B to 60% B. So here this is a linear change in the solvent composition. The two solvents are A and B, and you have the separation. Now this gradient can be convex or it could be a concave gradient. The current instruments are all automated, and you can make different gradients, and they also have preformed gradients. So in HPLC, equilibration is very important. That is, after a run or after the gradient, it must be equilibrated so that it comes back to the original condition for you to get reproducibility. Very often when we do HPLC, soon as the run is over, we tend to inject the sample again. But no, you need to have an equilibration so that the solvent that is passing through the column is the same as what you started with. So 2% B. So from 60%, it must come to 2%, and the column should be equilibrated. So this HPLC equilibration is very important. The next most important thing of HPLC is that it should be the viscosity of the solvent should be or almost equal to that of water. And you will see as the viscosity of the solvent increases, the back pressure of the column also increases, and this at times, because the instrument has a limit, the back pressure, the instrument will switch off. So the eluent viscosity is very important. So when you go back to use your HPLCs, please see the difference in the back pressure when you use methanol, when you use acetonitrile, and when you use methanol water, and also if you use isopropanol, you will see the differences. So we do not use very highly viscous and cannot use highly viscous solvents such as glycerol and glycol. So to summarize the thing, so we have seen the mobile phase, and we have seen how to choose the stationary phase and how they are used. Reverse phase HPLC or HPLC can be carried out at different scales. You can do it at the analytical scale, that is what we do in the laboratory. You can do it semi-preparative scale as in the research laboratories. You can do it at preparative scale by using large columns. And you see you've got industrial HPLCs, especially the pharma industry, which is to purify the material from grams to kilograms. So you have analytical, semi-preparative, preparative, and industrial chromatography. So in preparative, this is the same setup that you have, but you have very big columns which are there, and the fractions can be collected according to the peaks that you want. So this is used generally downstream to purify materials. See, analytes, after passing through the HPLC, have to be detected. So how are they detected? So each analyte has to be detected. So we use, or there is a detector as a part of the hardware. So the analytes will have different properties. They can either absorb UV light, they can either have the property of fluorescence with there, or they could have the property of charge, and so on. So different types of detectors are used to detect the analyte, what you see as peaks in the chromatogram. So the detectors that are commonly used are optical detectors. These detectors work exactly like the UV visible spectroscopy that we discussed the other day. So here the light beam, or the UV visible beam of light, whether it is through a tungsten lamp or through a xenon lamp, is focused on the flow cell, and depending on the amount of light that is absorbed and transmitted, a signal will be seen. The only difference between these online detectors and UV visible spectrophotometers are, here the detection is online, it uses a flow cell. So here the sample will be flowing through the cell, and it is not stagnant like the cuvettes that we use in a UV visible spectrophotometer. So some of the properties of the detector are: it should be sensitive, it should be highly stable and reproducible, it should have a wide linear dynamic range. We saw what this linear range was. It should have a very short response time, because you have a flow rate of 1 milliliter per minute. So the sample will be flowing through fast, and the detection response has to be very quick. Then it should be easy to use. It should have the same response towards all analytes. That means the lambda max should be uh, the same. It cannot be for the analyte, it cannot give different reactions. There should be a low dead volume. There should be no remixing of solvents, and these are non-destructive, because you can collect the sample at the end of the HPLC, as you have seen in the preparative HPLC. So all the detectors that are used have to give a linear response to the sample concentration. So as you increase the sample concentration, the response should increase, and this is measured by the area of the peak in the chromatogram. So the detector is said to be linear if the difference in response for two concentrations of a given compound is proportional to the difference in the concentration. And also, because of this linear response, we can use HPLC for the quantification, as you will see in the later slides. So the detectors that are available are refractive index. Yesterday we saw what refractive index was. This is a universal property. We can use the UV visible detector if the molecule has got a chromophore. You recollect what I told you about chromophores. You can use the photodiode array detector either in the UV or the visible range if it has a chromophore. You can use the fluorescence detector if, when it is excited at a particular wavelength, it emits light at a different wavelength. You can use conductivity. You can use evaporative light scattering detectors, the electrochemical detector, or the mass spectrometers. So you have already had a class on mass spectrometry, which the mass spectrometer is nothing but a detector. One of the most recent and commonly used universal detectors is the evaporative light scattering detector. In the UV visible spectroscopic detector, you know the principle. When any light, an electromagnetic radiation of a particular wavelength, falls on a sample, the sample will absorb a part of the radiation, and it will transmit the rest. And the transmitted light can be measured at a particular wavelength. So it is the same principle that we see in UV, the UV visible spectroscopy that we discussed on Friday. So the majority of the compounds, as I said, can be detected by UV visible spectroscopy if it has a chromophore. And we discussed what were chromophores. So if the compound has got any of these chromophores, you see the wavelengths at which it can be detected, and the molar extinction coefficients also are given. If the compound has no chromophore, then you could also use a technique called derivatization by converting it into a compound which will have a chromophore either in the UV visible UV region or in the visible region. The ELSD is one of the more recent detectors. It is a universal detector which can be used for all compounds irrespective of whether they have a chromophore or not. See, a UV visible detector can be used only if it has a chromophore. A fluorescence detector can be used only if the analyte exhibits fluorescence. A electrochemical detector can be used only if the analyte has a charge. But if any analyte has neither of any of these properties, which detector do we use? Those detectors are called universal detectors. And among the universal detectors that are used in HPLC are the refractive index or the RI detector and the evaporative light scattering detector. The mass spectrometer also is a universal detector, as every analyte has got a different mass. So if you look at the principle of ELSD operation, you see the sample when it comes out of the HPLC, it is goes through an atomizer to make it a fine spray. It is sprayed onto a plate. This plate is heated so that all the solvent evaporates, and then you have a powder. And we know that powders have the property of diffracting light. So if light, scattered light, is passed on to these particles will diffract the light, and that diffraction in the light which is measured as scattering and is therefore, when an analyte passes through the ELSD, it becomes a powder and it can be analyzed. How do we identify analytes in a chromatogram? Just like how you and me have got names, the compounds are identified by their retention times. So the retention time is taken for the peak to elute here. So you have the retention time. And the height of the peak is measured, and peak width is the distance from here to here, and this area which is shaded is known as area under the curve or area under the peak, which can be used for calculations. T naught is the void volume or void time before which no single compound can elute. So this is the time taken for the analyte to travel, for any analyte, minimum time taken for any analyte to from the point of injection to the start of the elution. So here, if you look at this acrylamide, see 1 picogram was injected, so you get an area of this, and the same acrylamide, if you inject more 10 picograms, you almost get 10 times the area. But the retention time remains the same to show that it is acrylamide, 2.85 minutes. So molecules are identified by their retention times. Sometimes the molecules are identified by their relative retention time, that is, the retention time in comparison to an internal standard. That is the retention time of the analyte divided by the retention time of the internal standard. And then you have a computer system to compute all this data, to calculate the area, and results can be analyzed. In reverse phase HPLC separation, the separation is described by four major concepts. One is the capacity, the efficiency, the selectivity, and the resolution. The capacity and the selectivity of the column cannot be controlled by you who are the user. It is controlled by the manufacturer. But the efficiency and resolution is controlled by the user. So we need to understand what is efficiency, because you want to get the best separation in the analysis. So resolution is the parameter. If you recollect yesterday, resolution was the time taken to see, it is the minimum distance to see two distinctive figures. Here, the resolution is a parameter which describes the separation power or the best separation in an chromatographic process. So how is the resolution calculated? It is calculated by looking at the retention times of two different analytes in the chromatogram. So if the analytes are that which elutes at T1 and T2, the resolution is given by T2 minus T1 divided by 0.5 into the width of peak 1 plus the width of peak 2. So if you get a resolution R is equal to greater than 1.5, as seen over here, you will see that you have a baseline resolution and you can separate compound A and B by 99.9% purity. If the resolution is 1, there is cross-contamination of A and B. And if the resolution is 0.8, we will not accept it in HPLC. So if you look at this figure, this shows you a compound. There are two compounds, there is no resolution. And finally, you have a resolution of 1, which is 0.8. We do not have a baseline separation. You have a resolution of 1.25. We do not have a baseline separation. So therefore, it is not acceptable. What would be acceptable is individual separation of the two analytes. So this is what resolution is. So resolution depends on the column efficiency, the capacity, and the selectivity. So what is column efficiency? So column efficiency is what you see in a column. If you see a compact column with a very sharp peak, it is efficient and the separation is good. So as you see over here, the column efficiency decreases as you see a peak broadening. So the sharpness of the peak is decreasing, and this indicates that the column efficiency is decreasing. Another way of maintaining or knowing how efficient the column is from day one till you have when you keep completely using is to go by what is known as the plate height or what is known as the theoretical plates. So you can estimate the theoretical plates of the column, which will give you the column efficiency. The higher the number of theoretical plates, the greater is the efficiency of the column. So you can determine the column efficiency of a column by injecting different compounds. The manufacturer will tell you how the theoretical plates are calculated. So we generally use uracil or acinaptine in a C18 column with 60% astronitrile water. You get a peak, and now using this peak, we can measure the height of the peak, the width at half height, and the width at the base of the peak, and you can calculate it by using any of these three formulas. The first formula is the common formula we use, which is equal to 16 into the retention time divided by the width of the peak whole squared. Or we can use the one at half width, which is 5.54 into the retention time by measuring the width at half height. So the theoretical plates will tell you the column efficiency. If after using it for a month or two, you find that you're not getting the same separation that you saw on day one, you can actually determine the theoretical plates. And if the theoretical plates has gone down from what the manufacturer has given, then your column has gone bad. And either you need to regenerate or take a new column. So what is the advantage of having a high efficiency column? You will see better resolution for peak identification and thing. So you see this separation, 11 different amino acids which are separated in 12 minutes. So high peak capacity for analysis of many components, and also high sensitivity at low concentration. So here is an example of naringin and camphorol separation. So if you look at what is seen here compared to what is here, here you have very good efficiency. The two have been separated, very good peak height. So this column, a C18 3 micron column of 100 into 4.6 millimeters, is much more efficient than a C18 5 micron. So here you see efficiency, as I said, increases with decreasing particle size, and this is a very good example. So resolution again depends on the capacity factor, and here your capacity factor is given by Va minus Vm divided by Vm. So here you have the two molecules and you can calculate it. Typically the compounds we use are toluene for normal phase, and as I said, uracil for reverse phase. And selectivity is, again, this tells you the equilibrium distribution coefficient for that. So it tells you how selective your separation is. Higher the alpha factor, the better is the separation. And selectivity versus efficiency. So compare these two chromatograms, you see this, there is low selectivity but very high efficiency because you have got very good peak heights. Here you have very high selectivity. These compounds have been separated very well, but you have very low efficiency because you have very wide peaks. And in HPLC, reverse phase or normal phase, what we look at, we need to get separations of this order. So general factors to increase the resolution are, you can increase the column length, you can decrease the column diameter, you can decrease the flow rate, you can pack column uniformly, use uniform stationary phase, decrease the sample size, select the proper stationary phase, mobile phase, and use gradient elution. Just to finish with some examples, you see, they can be used for the to detect adulteration. So generally in a fruit juice, the fruits which have higher value, the juice of those are adulterated with fruits of lower value. Cranberry and blackcurrant are two fruits which are known for their antioxidant potential, and they are highly prized. However, they are generally, the fruit juices are generally adulterated with elderberry. So how can HPLC be used to identify the adulteration of this, of either cranberry or blackcurrant with elderberry? So here an anthocyanin profiling can be done of all the fruits. So here you see this is blackcurrant. So here you're doing the anthocyanin profile of blackcurrant. So you have identified these four anthocyanins with these following retention times. Now, the cranberry anthocyanin profile is given by these four anthocyanins with particular retention times. What you see down here is the anthocyanin profile of the fruit juice under analysis or under testing. So what does this show? When you compare the profile of the anthocyanin juice with that of the juice which you are suspecting to be adulterated, when you compare, what you see is this peak here is too strong compared to pure cranberry juice. These two peaks you do not find in cranberry juice. So these are additional peaks which are not there in cranberry juice. And when you look at this, this clearly shows that these two peaks and the increase in this peak is due to elderberry addition. So different types of analysis like these can be used to detect adulteration. Okay, so HPLC can also be used for quantitative analysis, like how we use the UV visible spectrophotometry. But here you need to create a calibration curve. You can create the calibration curve by the standard calibration curve method or by using the internal standard method. So how do you do this absolute calibration curve method? You inject the analyte at different concentrations and you measure the area under the curve and plot the concentration versus the peak area, and what you get is a straight line. So the unknown area can be matched and you can determine the quantity of the analyte. You can also use the calibration curve by the internal standard method, where you inject different concentrations of the analyte and you inject different the concentrations of the internal standard and get the areas of the internal standard versus the target substance, and the ratios of the areas can be computed and plotted to give you a straight line. So reverse phase HPLC, by measuring the area under the curve or the peak, can be used for quantitative analysis. Generally, when you handle columns, you should observe restrictions related to solvents and pH range. You should never allow the packing material to go dry. You should not use solids or microscopic particles to enter the sample. That means your sample preparation should be perfect. You should use as low as a pressure as possible when you're doing the analysis, and you should not subject the column to shocks such as dropping them or to very high temperatures. So you generally store the column in what the manufacturer has asked you to store it, or you can wash the column thoroughly to remove all the analytes and store it in methanol and with the end caps on it and thing. So if you take care of your column, actually you can take care your HPLC column. These are pretty expensive, and so therefore we need to take good care of them. The applications of HPLC are numerous, and if I have to describe them, I might need a week or two. You can use it in addition to food analysis. You can use it for chemical analysis, to analyze proteins, peptides, in pharmaceutical analysis, in environmental analysis, in clinical analysis, as well as in the consumer products. So the next webinar I will shift gear from the basic sciences to the Food Safety Standards Act of India and the food regulations. So the next set of 8 seminars will be very critical, and you have 40% of your questions are going to be asked on the food laws. So you need to understand and read the Food Safety and Standards Act of India 2006 and the Food Safety and Standards Rules and Regulations 2011. So the next set of 7 lectures will be on the rules and regulations of India.